Okay, so the first one, I don't have my data in front of me. Let me pull up the data real fast so that I have that too. Okay. If you got an answer to the calculations for part one, I want to see what you got. What's your Q of cold water? What's your Q of hot water? Type it into Pear Deck for me. Now, I'm not going to hold you to this answer. You're welcome to change it as we talk, but I just want to see where you guys started. I see a very wide array of answers. If you took your own data, your answer won't match up with ours, which is totally fine. If you used my data, you should all get the same answer because you're all working from the same data. Okay, so yeah, I see a couple comments in here like, I have no idea if my answer is right or wrong because I have no grasp on how big enthalpy should be. That's true. And this will help you get we're looking at real enthalpy change. We're looking at actual heat that was transferred from actual bodies, solutions that we dealt with in lab. So hopefully that's another thing it'll give you is kind of a reference for what's reasonable and what's not reasonable. Okay. So on this one, when you're talking about prediction, if different amounts of hot and cold water are combined, the resulting temperature should be in between those two. So as far as looking at if your data is reasonable, your temperature should be between your cold and your hot water. You shouldn't get an ending temperature that is hotter than your hottest thing or colder than your coldest thing. So you should always evaluate, is my data reasonable?
I have a question about that.
Yeah, I'm ready.
So the final temp for the lab that when I watched your lab was actually just the average of the two, almost exactly. Even though there are different quantities, will that always be the case, or is that just okay? I didn't think that was going to be the case, but I was like, that's a weird coincidence if so.
Yeah, that's a fluke. If you use, if you're combining hot and cold water and you combine equal masses, then it would make sense that the temperature would be an average. But it's just a fluke that I didn't realize that happened. Yeah. So what's happening here, if you're looking at, hopefully you guys all did your drawings because that'll help kind of wrap your mind around what's happening too. But if we have cold water and we mix that with hot water, we're going to have energy transfer between the hot into the cold, right? There's our energy transfer. But we also have energy transfer from the hot water into the calorimeter. And so what you get is what your final heat transfer, what your Q total should be is Q of your hot plus Q of your cold plus whatever the calorimeter absorbed. If you look at the calorimetry lab in your lab notebook, it will have you calculate through, I think it's lab, let me find it. Okay, it's lab 12. If you want kind of a reference or you want that background information for calorimetry, it's lab 12. But what they'll have you do is they'll actually have you calculate how much energy the calorimeter absorbs. We ignore it. We do address it in the post-lab questions, but for our calculations, we actually absorb it or ignore it. So it really, even if you combine equal masses of hot and cold, your temperature shouldn't be an average because the calorimeter is going to absorb some of that energy. That's why before you start this, it's a good idea to kind of rinse out whatever you're using with either hot water or cold water, whatever you start with, so that your calorimeter is as close to your solution temperature as possible, because otherwise it's going to throw off your calculations. But yeah, it's a fluke. It shouldn't be an average. It won't usually be an average. Okay. So hot water, since the energy is moving out of the hot water should be a positive sign. Oh no, should be a negative sign, because your system is the hot water and the energy is moving out of your system. So whatever your QH is, it should be negative. Similarly with the cold water, if cold water is your system and energy is moving into it, your cold water should be a positive value. So this is the first check you should do on, are your numbers reasonable? Because you should get these signs, and if you don't, something's off. Okay, last prediction question. How will Q hot and Q cold be related to each other? If it's a perfect transfer of energy and there's no energy loss to the atmosphere or to the calorimeter, then Q hot should be equal to Q cold to the absolute value of those. They should have the same magnitude, opposite sign. Now they don't in this lab because we have heat loss. But theoretically, in a perfect system, the magnitudes of those two should be the same. The signs are going to be opposite. Okay, so let's look at the calculations. We want to calculate Q of hot water. So this is where your equation comes in of MC delta T. Again, if you look at the units for C, it should be joules per, I think, gram degree Celsius. So here's your equation right now, right? This is QM delta T equals C. So if they ever give you the units of C, you have your equation. Just a side note for you there. Okay, Q equals MC delta T. So if we are doing this for hot water, then every single variable should relate to hot water. It should be the mass of the hot water, the C for the hot water, and the temperature change for the hot water. So mass of the hot water, we have 95.5 milliliters, but we need that in grams. So did you guys figure out how to get it from milliliters into grams? For water, the density of water is 1 gram per milliliter, or it should be, right? So your volume in milliliters is your mass. So 95.5 grams. C, we're using 4.18 joule per gram degree Celsius. And then temperature should be the final temperature of the hot water minus initial temperature of the hot water. So you should go 58 degrees Celsius, which is the final for the hot water, and then 93.5 degrees Celsius, which is the initial for the hot water. And this is why your answer comes out negative. If you flip those temperatures, if you don't do final minus initial, if you do initial minus final, then your Q of your hot will come out positive instead of negative. Okay, so if you used my numbers off the video, your answer should come out to be negative 14171.2, and that's in grams reduces, Celsius reduces, that's in joules. And then you can keep 3 significant figures. This should be 0.0. So 1.42 times 10 to the 4 joules. Or you can convert to kilojoules, either way. Okay, so that's the process for the cold water. You're going to do the exact same thing, only you're using the mass of the cold water and then the temperatures for the cold water. Any questions on that process? For the cold water, I got 8087.4 joules. Okay. Okay, so some of you are changing answers on Pear Deck, which is totally fine. Like, if you didn't set this up correctly, it's worth running through it on your own. Even maybe just do it now, write down this now, although I'm recording this and I'll post the recording for you also. But like maybe tomorrow, like run through it, or tonight or tomorrow morning, like run through it again and see if you can do this, or go find a practice problem like enthalpy transfer, hot versus cold water. It'd be worth running through it again. So some of you are changing answers, which is great. But what I want to know is if you have a question as to why you're changing those answers. If you have a question, let's deal with those questions. And those of you who did your own data, if you used like ballpark similar masses and temperatures, then your data should be around the same area. So if you got like the same order of answers, like times 10 to the 4th or 5th or 3rd, then you can be confident that yours are reasonable. Yeah, 4.18. You don't have to memorize that number. I'm pretty sure it's on your reference sheet. If it's not on your reference sheet, they'll give it to you in problems. But I will tell you by the end of this chapter, you're going to have that number memorized, which is nice because then you don't have to look it up. It's always the specific heat for water, and it's almost always the specific heat for solutions. As long as the solution is like diluted enough, the specific heat of solutions is the same as specific heat of water. Good. Okay, so a lot of you are feeling confident on this one. So I'm I want to do part 2 now. Where are we on time? Yeah, let's do part 2, but I don't want to walk you through it. I want you to just try it. Try part 2. Let's try it right now. And then ask me questions as you go. Again, you have to align your context. If you're doing heat of the metal, every variable has to be of the metal. If you're doing heat of the water, every variable has to be for the water. So go ahead and try it and let me know when you run into questions. Yeah, C is going to be the same because you're still dealing. C of water is the same. You don't have C of metal. You have to find it. Oh, did I not put that in there? Yeah, you have to find the C of the metal.
How would you find the C of metal?
Give me 1 second to type a question, and then we'll deal with that next. I mean, type an answer to a question. Okay, so give me 1 minute. Okay, so Kaya, have you calculated Q of the water yet?
Almost. Once I plug in, I'm almost done with that one.
Yeah, that's the first step. You need that first. So finish that, and then we can deal with the metal. Okay. Did you guys get that? No one typed an answer, so I have no idea if you guys are there. If you guys are stuck. Okay, so that's the Q of the water. Now, I forgot to talk about this on the last slide, but did Q of the hot water equal Q of the cold water equal the negative of Q of the cold water? No, they were not equal. One was like 1.4 times 10 to the fourth, and then one of them was like 8 times 10 to the third. So they were definitely not equal. And the difference between them is what the calorimeter absorbed. So notice that Q of the cold water was lower, was less. That's because some of the hot water's energy went into the cold water, but some went into the calorimeter. So on this problem with the water and the metal, we're ignoring whatever the calorimeter absorbs. We're assuming that all the water goes into the metal. If it doesn't, then whatever the water gives off, oh no, it's metal. Metal's giving off the energy this time. Whatever the metal gives off, the water plus the calorimeter absorbs. But we're ignoring the fact that the calorimeter is going to absorb some energy. We're going to pretend like it's a perfect transfer. And so if Q of the water is 1.42 times 10 to the third joule, then Q of the metal should be the same with the opposite sign. So what is Q of the metal? Well, it's negative 1.42 times 10 to the third joule. That's how you get Q of the metal. Now, can you figure out what the specific heat of the metal is?
So then would the heat of the metal just be the negative 1.4 times 10 to the third?
Yep.
Okay.
Yeah. Okay, find C of the metal. What's the specific heat of the metal?
Would you use the same temperature change of the water? Because, you don't find the final temperature of the metal.
Yeah, good point, Kaya. So we don't actually stick a thermometer into the metal, right? But what should the final temperature of the metal be?
The same as the water.
Yeah. So we assumed we brought the metal up to boiling, and we assumed that the initial temperature of the metal was the initial temperature of the boiling water, which I think was 93 something. 93.1. So in the same way, once you drop the metal into the cold water and they equilibrate, then the final temperature of the metal should be the final temperature of the water you drop it into. Yeah, like I said, easy equation, but tricky to figure out all of these little things about the context, right? Good questions, you guys. Keep them coming. What other questions do you have? Once you get a specific heat of the metal, type it into Pear Deck or the chat. Okay, I see answers rolling in. So Okay, should we set up something like that? I got 0.410. Anybody else get that? Q water. I thought Q water was negative. So Francis, I'm answering your question. Good question. Okay, so Q of the water, you got to think of the context in this one, right? We have a piece of metal here, and we have water here. So the metal is hotter than the water. So in this case, energy is going to go from the metal into the water. So if water is your system and water is absorbing heat, water is going to be positive. So it all depends on the scenario. Like in the last one, Q hot was negative, Q cold was positive. In this one, metal hot is positive, water that's cold is negative. No, that's opposite. Metal that's hot is negative, water that's cold is positive. So it all has to do with what's absorbing and what's giving off. Yeah. That's why drawing the pictures helps. That's why I wanted you to draw pictures at the end of all of these, because it kind of straightens out your mind as to like what's giving off the energy and what's taking in the energy. Okay, we are at the end of our class, but here's what I want you to do. A, you can now go look up what metal this is. You literally can type in, go find a chart of specific heats of metals, and you can figure out what our metal was, which is pretty cool, I think. B, try the calculations for part 3 before you get to class tomorrow, so that you kind of have this idea of like, yeah, I can get to the end and I'm pretty sure I did it right. Or I can start it, but I get stuck here. Here's where I need help. Like find your point of confusion and bring it to class tomorrow. And I'll stick around for questions, but you're welcome to go.